Last video, we looked at the concept of work and how essentially applying forces to a particle when that particle moves can cause increases in kinetic energy or decreases in kinetic energy. And essentially, those forces are doing work on our system of a particle. And we looked at so one case, but three different sort of ways this happens. If we have some force that's in the same direction as our displacement, the direction the particle is moving, we have the sign of that force is positive. It's adding kinetic energy to that particle, and we can calculate it just by the magnitude of the force times that displacement. If the force is off at an angle, but still sort of has a component in the direction of the displacement, it's going to be positive, but we have to sort of take that, look at the component of the force that's in the same direction as the displacement. If the force is perpendicular to the direction that the particle is moved, the direction of the displacement, that angle is going to be 90 degrees, and the force does no work, which sort of makes sense. This force wouldn't cause this particle to speed up or slow down in that direction, so it does no work. And the last case, if the force has a component or is in the opposite direction of that displacement, that work's going to be negative. It's going to remove kinetic energy from that system. And you can see that just from the cosine theta term there. This all came from the fact that essentially we were looking at force times displacement times cosine theta was how we calculated the work done by a constant force, right? And if that theta was 0 to 90, it's positive. If it's 90 to 180, it's negative. If it's at 90, it's 0. Now, why is this the case? Well, it turns out what this actually comes from is what's known as a dot product, where if we have the work done by a constant force, the work is equal to the force dotted with that displacement. So in this video, we're going to spend just a bit of time doing the math and getting used to what is a dot product. All right. So turns out there are two ways you can multiply vectors. Remember, vectors have direction and magnitude, right? And there's two ways we can multiply them together. One is called scalar product, or that's the one we're looking at today, also known as a dot product. And the other one that we'll look at later in the semester is called a cross product, or a vector product. Now, the scalar product and the vector product, if you think about it, we have two vectors, A and B. If we multiply them together, we can think of getting two different types of results. One, we get a scalar. We just get a number that has some magnitude. If we do the other, we get a vector. And that's sort of the distinction between these two. The notation is if I want to take A and B and multiply them together using the dot product or inner product or scalar product, there's a bunch of names for it. I just A dot B. If I want to do the cross product, you use A cross B. And the result, and again, the result of the dot product is a scalar. The result of the cross product is a vector. Now, the way we calculate a dot product, there's a couple ways. One, I like to think of sort of as a geometrical representation. But if we take this dot product, we end up with this, right? The dot product A dotted with B is equal to the magnitude of A, so how large that vector is, times the magnitude of the vector B, times cosine the angle between those two vectors, right? So if I have this vector A here and this vector AB here, and they're off at some angle alpha, I can just plug and chug those numbers. And the way of calculating this really lends itself well to if you were given the vectors, if you recall, vectors have magnitude and direction. You can describe them in terms of just give me the magnitude and some angle relative to some direction, or we can give those vectors in terms of components. Well, if you're given those vectors in terms of the magnitude and direction, this calculation is pretty much straightforward. I mean, you're given these numbers, the magnitudes, you can determine that angle between them if you know the angles for each individual vector. And you can see how this kind of is consistent with everything we saw with work. If we have two vectors that are parallel, they're in the same direction, it's just the magnitudes of them multiplied together. If they're at some angle between 0 and 90 degrees, it's going to be positive because that cosine theta is going to be positive. And essentially, we're looking at exactly what we were looking at with work. Remember, work done by a constant force was force times delta r, the displacement, times cosine the angle between them. And we got those same things. If A dot B is, if A and B are perpendicular, we get 0, and then if the angles between 90 and 180, we get negative values. So again, nothing new here. We've just kind of lifted up the hood and gone underneath into why we have this equation for the work done by a constant force. And it's because we calculate it from a dot product between the force and the displacement. Another way to calculate the dot product is with components, right? So if you, we have what we've been discussing for, if I have force dotted with displacement and I take the dot product between those two, I get the magnitude of the force, the magnitude of the displacement, and cosine the angle between them. That's really well and good for vectors where I've been given the magnitude and direction, but if I've been given these two vectors in terms of their components, the x component and y component, I can calculate those that dot product by just multiplying the components together and then adding them. So you get this, right? If I want to take A dot B, I can just take the x component of A, the x component of B, multiply them together and add it to the y component of A and the y component of B. And this is a really convenient way to do the dot product if you've been given components. But we should be really comfortable with both. And hopefully through the homework and the synchronous sessions, we'll go through some examples that kind of walk us through that. Here's a pretty straightforward example, and I'm going to use this to show that both dot products, both methods of calculating these are the same. So I have two vectors, vector A, vector B. Vector A is, has a magnitude of 3 at some angle 30 degrees above the x direction, and vector B has a magnitude of 4 and it's in the x direction. So if I want to calculate A dot B, how do I do this? Well, we have two ways. In the first way, that sort of geometrical representation, this is just going to be the magnitude of A times the magnitude of B times cosine the angle between those two vectors, which in this case is going to be 3, the magnitude of A, times 4, the magnitude of B. Let's put some brackets here so we can get clear, times cosine the angle between them, right? This ends up being essentially 10.4. So 10.4, right? If we look at the other way we could have calculated this, A dot B, if we did this sort of algebraic way where we're just multiplying components, we have to determine, what AX and BX are, because this, again, we can look at as the X components added, multiplied together, plus the Y components multiplied together. So the question is, well, what's AX? Well, AX is just the component, I'll do this in red. AX is the component of A in the X direction and AY is in the Y direction. So AX is going to be equal to the magnitude of A times cosine this angle 30, right? And that gives us our projection. So that's 3 cosine 30. And the AY is just going to be 3 sine 30. It's the opposite side to that angle. Hopefully we're very comfortable with breaking things into components by now. What about B? Well, B is entirely in our X direction, so BY is 0 and BX is just 4, the full vector. So if we go back over here and do this calculation, AX is 3 cosine 30, BY is 4, AY is 3 sine 30, but that's multiplied by 0, the y component of b. So this whole term goes to 0, and we end up with 3 cosine 30 times 4, which is the exact same answer we had over here when we did it the other way. So again, two ways of calculating cross products. One, like I say, I like to call sort of a geometric way of approaching it when you're given vectors with magnitudes and directions. The other, when you have things in components, can kind of be a more straightforward way. Hopefully you're comfortable with this. Perhaps you've seen it before. This is how we're calculating the work done by a constant force. So work done by a constant force is F dotted with that displacement, delta R. And that's where we got everything from the previous video. This has been a quick one. And in the next video, we're going to look at the work done by the force due to spring in that. So if you have any questions, email me, talk to me in the synchronous sessions, and I will see you then.